You are in the mission engineering session, and there's a lot of really good talks in this session. So I'm really excited to hear these talks, and I think everyone will really enjoy them. First up, it's my pleasure to introduce Dr. Cesare Guariniello from Purdue University, and he will be presenting updates on his research task WRT-1002, titled Approaches to Achieve Benefits of Modularity in Defense Acquisition, Part 2. With that, I turn it over to you, Doctor.
Okay, thank you. So I hope everybody can hear me fine. It's a pleasure to be here. Good morning, good afternoon, good evening, depending where you are watching this from or when you will see it. As Russell said, this is a presentation, actually second presentation at SSRR about WRT-1002. And this is actually a final presentation for this project, sponsored by the ODASD for System Engineering. And as you can see on this slide, this is presented on behalf of a whole research team. So this was a 4-year effort that covered 3 research tasks under CERC sponsorship, RT-163, RT-185, and WRT-1002. Dr. Dan De Laurentiis served as PI for this project, and then we had 4 co-PIs, me, Charles Domerkan, Tom McDermott, and Gary Whitus. They were actually all instrumental to the success of this project. Since this is an overview of the entire project, of everything that we did during these 4 years, I will actually spend a few slides to talk about what we did in the past, how this entire project evolved, and then I will show in more detail what we did this last year. This project actually ended around March. So first of all, what is the problem that we started from? This project is approaches to achieve benefits of modularity in defense acquisition. So the first thing is what kind of problems we are addressing that we can use modularity in. What we looked at is multi-domain battle scenarios, complex system of systems, and complex mission engineering problems where the complexity is due not only to the size of the problem, but also to the interactions, to the dynamics, to the fact that this is an evolving scenario. So in this context, DoD had some challenges for acquisition. We want to be able to save money, to not waste money. So we want to affordably address new threats that can be emerging. We have the components can become old over time, so we also have to plan technology upgrade. And of course, we know that these systems are tightly coupled, they're integrated. So using modularity can bring some benefits because of course we might be able to have more flexibility, more reusability. Even modularity though poses some problem. There's a large trade space. First of all, where do we put our modularity? Is it at the mission level? Is it at the system of system level? Is it modularity in individual systems? And second, we need to consider competing metrics. We need to consider not only cost. Yes, we want this to be affordable, but we also want a certain amount of performance. And if we're thinking about dynamics, we want to be sure that this will also work for the future. So we want some flexibility. And of course, some more source of complexity comes from the fact that there's a lot of uncertainty in these systems. Uncertainty in performance and cost, uncertainty in future missions, and so we also want some gradual development of our systems, our acquisition. To expand a little bit more on why a modular open system approach, MOSA. MOSA is an initiative started by DoD. It encourages adoption of modularization and open architectures. This will improve speed of delivery, flexibility, and it will reduce cost. So it will bring some cost reduction. In the last few years, we already had some findings from previous research tasks. The 2 main findings were that modularity is not a goal. We don't do modularity for modularity's sake. This is a means to achieve some benefits and want to be able to measure these benefits. The second important finding is that doing good MOSA, it's not only about how we architect the systems, it's not only how we acquire, but also entails having readiness in our organization. Are we ready to apply MOSA principles? Are we ready to use modularity and open system architectures? And if we're not, what we should do? So the objectives that we had in all these research tasks were to develop strategies and tools to be able to be successful in this ecosystem where we want to use modularity and open systems, to identify guidelines for implementation of these strategies, and to be able to quantify the benefits, not only in the technical aspects, but also in the managerial aspects. So what do we do and what do we gain by using MOSA? So the first thing we did when we started these tasks in 2017 was an initial workshop where we gathered government, military, academia, and industry to listen to their needs, to their requirements, and to figure out what was the state of the art. So we gave an initial characterization of what the MOSA ecosystem did. And we followed the workshop with some interviews to program managers to learn about their perspectives. And here's where we found those key findings, among which I already mentioned a couple, which is MOSA is a means to achieve benefits, not the end goal, not modularity for modularity's sake. We also found some other important points, which are that early stage acquisition process is key to modularity. You want early support mechanisms in place. There are some program managers that stated that if they come late in the life cycle, they cannot really apply any MOSA principle because whoever managed the program before they did not make the project ready to have MOSA. So organizations need to be ready to deal with these solutions. And the way we want to support them is with some tools that can assess what are the consequences of making certain choices. And so the two main products that we had in the first years of this effort, first we started with a prototype decision support framework, DSF, where we were trying to tie together inputs, which are the context, the environment, the details of mission, the organization, and the resources that are available in terms of system, interfaces, interactions. We wanted to tie these inputs with outputs in terms of cost, risk, and how much we can adhere to MOSA principles. The way we did that was to use cascading matrices, similar to QFD, and house of quality shaped. And these cascading matrices will create a visual analysis of how these inputs translate to the outputs throughout the program lifecycle. So this was something that established a path forward to collect data, create a database of case studies. The second deliverable that we had is a program manager guidance document. This was based on lesson learned from our interviews, from our workshop. And the way we did was we created a practical instrument. This is a collection of case studies and lesson learned so that a program manager can consult this and find similarities with the kind of problem that they're addressing and figure out what other program managers did with these issues. What were the lessons learned, or is there something that is still unaddressed? What will be the difficulties that they might encounter in these projects? So here, again, we underline the important points. Is our organization that needs to use this solution ready to deal with it? Do we have the appropriate artifacts from systems engineering? And do you have that early in place? Other very practical ideas, for example, how different ways of contracting can support most objective. So this was the start point, the baseline point for WRT-1002, which is this year's final effort in this research. We had a few objectives for this WRT-1002 MOSA research. First, building upon the previous effort, refine our decision support framework, which was still in a draft form, and made it a usable tool. And this decision support framework needs to have both quantitative analysis, focus on cost, risk, schedule trade-offs, and the qualitative analysis based on the cascading matrices like we did in the beginning, which will show the relationship between input outputs, like what are system of systems, where the capabilities come from in our project, so that we can also start discussing about organizational structure. We want to translate knowledge from specific programs into this decision support framework, and then have tools to explore trade-offs between metrics of interest and, of course, validate and verify our DSF. So if you look at the plot at the bottom, on the left side, based on inputs, type of missions, like remember we started from our problem of multi-domain battle scenarios. Based on case studies, we want to build a knowledge database of cases and important ideas. This knowledge database and the type of mission that we have as input will provide requirements to one of our tools, which is called Robust Portfolio Optimization, RPO. This tool generates alternative architectures, generates a series of portfolios of collection of systems that provide the requirements for our mission and have different cost, different risk acceptance, and of course different features for what concerns modularity and open system. Some of these architectures are modular, some are not. Some have modularity only in certain components. What we do once we have these alternatives, we start our analysis, which is both the qualitative analytics with our cascading matrices. And here we have another input, and you can see in the central part, heuristics on MOSA benefits. So we got some information on like what are these benefits that come from MOSA, and are they present in our architecture or not. And we have our qualitative analytics, which is system of system analytics. And you will see here a few acronyms in the figure: SODA, SDDA. Those are all tools that provide some analysis on different aspects of our architectures. For example, where are the bottlenecks in development, or where are the risks during operation? Is our architecture robust or not? So as you can see, we are trying to explore different aspects of our architectures, not just the cost or the baseline performance. All the architectures provided by RPO satisfy our requirements. We want to see which are better, and better means comparing them against multiple metrics, which sometimes are competing. So in the end, our outputs are, first, for the qualitative part, adherence to MOSA principles. Are we following these principles? Can we do that? And what we should do to be sure that we are capable of addressing these needs. And the other output is the quantitative output, comparison of cost, risk, flexibility. And I will show in the next few slides how we did this. Meanwhile, while we were developing our decision support framework, we didn't stop our learning and our interaction with other stakeholders. We participated in workshop with the Modular Open System Working Group, MOSWIG, where we learned about the MOSA pillars by Naval Information Warfare Center. We learned about NDIA guidelines for modularity. We studied the Victory program, which provides standard electronic system architecture for ground vehicle. We look at MBSC, model-based system engineering for MOSA. We actually presented a paper last month at Cesare 2020, implementing a MOSA decision support tool in a model-based environment. And this includes lessons learned from Mark Blackburn's work in RT-187. We look at the open architecture assessment tools. So we kept our learning here. Now, to be more specific into the tool and the DSF, the form that it has now, to be able to verify and validate our tool, we built a case study in Decision Support Framework 2.0. And this case study is a multi-domain battle scenario. It's an amphibious warfare system. The requirements are based on mission engineering. And what we did is as in the figure that I showed a couple slides before. We use robust portfolio optimization to identify alternative sets of systems or architectures that provide requirements for our mission. Then we use system operational dependency analysis tool, another tool that we developed within CERC, for analysis of operational criticalities. We developed our cascading matrices of capabilities, and we analyze what are the applicable MOSA principles. In this case study, we showed that this is useful to study different future missions, for example, so we can change our requirements and see what of our systems that we had in our initial portfolio can be used in different scenarios. So we look at the flexibility. And of course, we are looking also at choices on modular versus non-modular architectures. What are the differences in terms of performance and cost? Our input for now is on Excel spreadsheets. And so in the next few slides, I will show how this input and output work. First of all, and this is not a mistake, the writing the text is very tiny because I didn't want to show the exact problem. I only want to show how this tool is used. First of all, we need a database of what are our available systems. And you can see that on the left side. And each system requires some support. For example, some vehicles need operators. And of course, if you got modularity, some system might require some other system because it's a modular part of a complex integrated system. We can have support in terms of transportation, support in terms of delivery. And we list all of them in our inputs. Each system is also associated to system capabilities, cost, modular properties, and we also have our uncertainty. So our performance is not a fixed number. There's uncertainty on performance. There's uncertainty on cost. Second part of inputs to the decision support framework. In the first spreadsheet, we had system capabilities. Now we want to know what are system of system capabilities as function of system capabilities. System of system capabilities are expressed in form of, for example, air superiority or land control. What kind of capabilities we need at the level of systems to be able to have this high level requirements? Like if we want to have land control, what do we need? We need certain system capabilities. And so this way we have this hierarchical structure of requirements coming from our mission, which are not expressed immediately in terms of individual systems. We have to have this relationship. Then we have a series of constraints. Systems can be incompatible with each other. We can have a limit to the number of systems we can select. For example, I want at most 20 different land vehicles. We also have some other constraints that we call conditionally required systems, which means if I want system X, then I need to also have system Y. So we added these constraints so that we can be able to address multiple different problems with the same structure. We also have a graphic user interface. In the opening window, the user can just select if to use our case study from our database or create their own scenario. And I will anticipate what I will say later. We are already using this decision support framework in other projects. So we are creating different missions and different databases. In the main window, the user can select what system of system capabilities will be used for optimization of the architectures. As I say, we can study different missions, either current or possible future threats. And so we want to be able to select different requirements, different mission requirements that we have. The user can also select where to put the uncertainty. We might have some capabilities that have no uncertainty and some capabilities who have uncertainty. And then we want to study a range of different architectures. So the user can also input a range of risk aversion levels that they want to have. There are architectures that are more risky in terms of uncertainty. They might not be able to give our performance as we want, and the user might not accept that. So the user might have a higher level of risk aversion, and they can input their preference here, and they can also input their cost limit. So all the different architectures will have a different budget, because again, we are trading off cost performance metric. Finally, the user can input weights for the optimization function. If the user select more than one system or system capability or mission capabilities, some of these capabilities might be more important, and the user needs to be able to express that. And finally, since we were studying modularity versus no modularity, there is a choice that the user can make of imposing that modular system are present, or actually deciding that modular system cannot be used. Once the user adds all these inputs, thank you. Once the user adds all these inputs, we got results. The first result is in terms of portfolios. Which are the portfolios? What is their cost? What is their performance? So we can see a Pareto front of cost versus performance, given the level of risk we accept. And of course, more cost, more performance. So we can spend more and get better. We can visualize the portfolios and their dependency. We can visualize what are the systems that are selected in architecture and which systems provide support to other systems. We can also select only part of the network. For example, the bottom right figure here is the subset of systems that provide transport capacity. Third input, the qualitative cascading matrices. Where do the capabilities come from? Which system is providing the mission level capabilities? Which system of system capabilities, where do they come from? So this is where the user can look at, okay, now you tell me that this portfolio will satisfy my requirements. How does that work? Where does this exact mission requirement come from? And then we have our external analysis with tools that we develop in other Circ projects. For example, systems operational dependency analysis studies the operational criticalities. What you see here, this colored matrix, is called a disruption impact matrix. And what it shows with colors is if we have failures or disruptions in various systems in our portfolio, which of them will cause the highest damage, which would be the red cells. So in this case, the advanced targeting system had red cells. That means that there was a system that, if disrupted, would cause us a much danger of losing our entire mission, while other disruptions are either not too bad, which is the green cells, or they can only provide limited damage. So we can also see how robust is our architecture. And finally, we analyze the applicable MOSA principles. We look at our systems and the corresponding benefits from MOSA principles. We also can see that in a graphical representation. I think next slide will also answer a question that I saw in the question and answer. Some comments on modularity in our DSF right now. Currently, the benefit of modularity comes from database, which is based on our lesson learned from Program Manager guidance document. And it's not quantitative, it's only qualitative. It includes our lessons learned, it includes our constraints about support systems, cost and performance, but doesn't create a new metric. It only says this architecture with this modularity is better because it's lower cost, higher performance. But we are not making a metric for modularity. We are not saying how modular this is. We're only saying, well, with these specific systems, you can have this benefit from modularity. You can apply certification of conformance. You can apply better interoperability. You have more flexibility because this system is usable in 10 different missions. So it's better performance and lowers your cost, but we're not creating a new metric. So what we want to add here is actually something different, which would be what are also the managerial requirement, or what is the cost of increasing modularity. So this is for future work. So in conclusion, this research in these few years highlighted a few needs, especially including MOSA considerations up front, and evaluate in our program which systems and program can benefit from MOSA. So if we're not ready, some program might not benefit from MOSA. Or even if we use the DSF, we can see that in certain missions, it's better not to have modular systems. So we develop tools to assess performance in these scenarios and to trade off cost and risk under different choices for modularity. We develop our decision support framework that generates portfolios given database of systems, generates Pareto fronts of cost performance for different level of risk aversion, and also provides further analysis, operational criticalities, qualitative assessment, most analysis that I can, as I already said, we can improve upon. Right now we have transition plans. We are developing and refining the DSF in other projects, even within CERC. We got some interest from entities in Moswig, so we also want to collaborate with them. And right now we are also working on dissemination of this work to identify potential partners for future case studies. And with this, I thank you for listening to the presentation.
All right. Thank you for the talk, Dr. Guariniello. That was a very excellent highlight of the benefits of MOSA architectures and also the tools. Looks like some pretty exciting stuff that'll be very beneficial to the DoD. So we'll turn it over to questions. If you have any questions, please feel free to type in the Q&A. The first question is from Robert Schur. And the question is, the DSF tool available for evaluation by industry users?
That's a very good question. Until now, we use the DSF only internally with CERC and DoD, but I think we would be really, really happy to make the DSF tool available to industry, because it gives us more VMV and more case studies that we can use, and of course we can trim or tailor the tool to what our needs in industry. So I would like to be in touch.
Okay, excellent. Another question from Robert Lewis is, does this mission model deal with the multiple direct attack strategies, i.e. fixing force and maneuver force? Does it also incorporate different environments such as mountain, plains, desert, etc.? And finally, does it have the ability to assess systems in the different strategic roles and phases of each of the services? For the Army, this would be shaping operations, for example, pre-combat peace or direct combat, and consolidation of gains post-combat.
Excellent question. So for the multiple direct attack strategies, that goes into the mission requirements that we put. So yes, we had that in our model. We didn't have, we had different environment. Oh, sorry, we didn't have different environment, as in like this was a multi-environment because it was an amphibious scenario, but we ran the case study only in that amphibious scenario, so we didn't consider the difference between the different environments. But the model, the framework will still be there. So what I mean is that we should only change the inputs that we give to the tool. Same goes for the different strategic roles and phases. So in some of the projects that we are using the DSF right now, we're actually looking at different phases. And for each of them, we just have a different run. And then we go look at, in our portfolio, which systems are useful for multiple phases. So it's a matter of changing the way we give the input or the requirements and running the different cases for the different phases.
All right, excellent. That's all the typed out questions we have, but feel free to continue asking. We still have about 10 more minutes. I had a question myself. I've definitely realized the benefits of open architecture early on when I worked for a project that did not have an open architecture, and we ended up having a large portion of our budget dedicated to parts obsolescence. In my experience, I found a lot of things that say they're open architecture are not necessarily open. And so you discussed that your open architecture assessment tool, you can kind of determine the level of modularity. But it seemed this is mostly, I guess, my question is this mostly a manual process where you gather information and then input it into a database, or is there an automated approach to use the tool to determine kind of the openness and modularity of different architectures?
So unfortunately for now, until we established and create a database, it's mostly manual. So we have to still input many information because there is not a way to uh, understand how MOSA or how modular or how open something is unless we have underlying data, which is what we're using now. So when we do our MOSA evaluation, is just we have a list of these systems and we know that, for example, some of them are certified from a third party, or some of them are modular and they require a certain way to use them. But there's no way we can already automatize that. I see a question in the chat from Monique. She's interested to look into how the DSF could be used to address benefits of interoperability. This is very important. So what the DSF does right now is analyzing the benefits. So it compares architectures where, for example, everything is pipelined and there is no interoperability or there is not much support, can compare this with architecture where we have this interoperability between systems and platforms. So we can impose to have architectures where this support is, for example, somehow modular, and so we have this interoperability, and we can compare cost, performance, and risk. And this is how we would address that.
All right, we'll still have a few more minutes if anybody has any last minute questions. Otherwise, we can get an extended break for a few people. I guess I did have one other question, there's another question from Robert Lewis. And the question is the ILITES assessment, how are the various attributes compared against one another? If an architecture is assessed as being more modular and less capable, are these equally compared, or are there graduations to this?
Other very good question. Since we do not know how the users want to evaluate this, this is why we provide Pareto fronts. So we tell the user, this is your attribute, and then the user can decide what to do with that. The big problem is modularity, because it's much easier, of course, to compare capability and cost and risk, because we exactly know, it's like, this is the cost, this is twice the cost, and you get 1.5 times the performance, and the user can decide whether to accept that or not. But since we don't have a quantitative metric for modularity, it's hard to say this is better because it's more modular. And that's why we are trying to avoid, as I said in the beginning, to use modularity for modularity's sake. We are trying to evaluate the outcome of having modularity or not, so that we are comparing quantitative measures. And again, we give the user freedom to decide what to do with the results. So we provide them with the entire Pareto front for the various trade-offs.
Excellent. My question was kind of along the same lines. Another question that I had. So obviously there's a lot of benefits to modular open systems architecture approach, but there's also some architectures, most architectures that are kind of becoming more mainstream. One example would be for the Air Force, the OMS, Open Mission Systems Architecture, but there's plenty others. Are there plans to kind of plug those into your tools to assess kind of which existing architectures the most architectures are compatible with?
That's actually something that we didn't think yet about, which might be a good idea because, of course, besides including case studies, we also wanted to include something that's already existing. That's why we were looking at MOSWIC, we were looking at OAAT. I don't think we looked explicitly at OMS, but of course, that would be actually probably the best way to do to verify and validate our tool to check is like, does it go along the line of OMS?
Okay, excellent. Yeah, glad I could throw a suggestion out there. Okay, well, it looks like that's all the questions we have. Again,
I see another one in chat.
Okay.
Did you have any thoughts on improving OAAT? Actually, I'm not the person in the group that worked on OAAT, so I don't have many details about that. I think we use that mostly as input rather than output. So we use that something that look at what the Navy is doing, look at what people that are using OAAT are doing, so that we can kind of use that as our metrics for MOSA evaluation. But I think the use of DSF should improve OAAT in terms of making it more quantitative. Right now, OAAT is the program manager gives the score based on what their opinion is, and DSF should make that a little more objective.
Looks like we had actually a couple more questions pop up. One is more a comment from Monique. She says, I concur with partnering with OMS. And then another question from Robert Lewis asks, is there a paper that outlines this approach?
I don't think we have a formal paper on the DSF yet. There are papers on MOSA. We have a journal paper on the initial effort, the first year of this effort. So I think it might be time to have a second one, but I would be glad to send that publication. I think it should be on the CERC website together with the deliverables from this project. But in case there is not, I can send it to Robert directly.
Excellent. Seems you're a few seconds ahead of me on seeing the questions. We'll give it another 30 seconds here if anybody has any more questions, and then we'll wrap up.
Well, thank you to all the people who asked questions and made comments.